Good evening, everybody. Thank you so much for giving me the opportunity to speak with you tonight. You probably noticed from the title on the slide that it doesn't say high-rise buildings, and I'll explain to you as we go on why we had to evolve from that concept. So I just want to tell you from the start that my perspective on this is most probably biased, and it's biased because firstly, I'm not an engineer, and I'm looking at this from a probably diametrically opposed point of view than you. I've in my 34th year in Dublin Fire Brigade, and my specialist instructor training is in compartment for behaviour, tactical ventilation, breathing apparatus, and of course high-rise firefighting. My first exposure to high-rise firefighting in terms of training was in the Petronas Tower in Kuala Lumpur. So it's like learning how to fly a little bit in an F-16. So that was an interesting experience. So what I really want to talk about is the project that I'm leading in Dublin Fire Brigade regarding how we're going to really deal with the changing built environment here in Dublin. And basically what we would try to do is to examine the problems associated with tall and complex buildings firefighting. We also identify opportunities for firefighter skill and knowledge development. That's a really political way of saying to somebody to really figure out what we're not very good at. We also wanted to implement a robust procedural and policy-based process that firefighters could operate safely in the changing modern built environment. So that was the overview of the project. And basically, the very first question we had to ask is, what is a high-rise building? So we initially started by looking at Dublin City Council's development plan running from 2016 to 2022. And if you look at the bottom of that table, they estimate that low-rise runs up to 28 metres, medium rise up to 50 metres, and high-rise buildings over 50 metres. So when we started to look at that, the first thing that struck us was that the National Fire Protection Association in the United States will classify a high-rise building at over 23 metres. So immediately we started to think, why is one of the most experienced organisations supporting fire officers looking at high-rise at a much lower level than Dublin City Council? So to help us understand that a little bit better, we looked at the way that they were zoning the city. And if you look at the green splurge on that diagram, that's the area that's zoned for up to 28 metre buildings. The two purple circles is where Dublin City Council are going to build what they consider to be high rise. So that would be at Houston Station and down at the end of the quay wall there at Capitol Dock. And the other parts of the city in the reddish, pinkish colour, they can build anything up to 50 metres. So in essence, the entire city is going to become a tall and complex city from our point of view. So really we had to have a conversation with Dublin City Council because they really pay for the fire service in Dublin. And we had to have the conversation really was, how does the fire service define high-rise buildings as opposed to their perception? So the start point was our nearest neighbour in the UK, and their generic risk assessment say that for the purpose of this assessment, a high-rise building is defined as a building containing floors at such a height or position that the deployment of external firefighting equipment and rescue operations may not be feasible. So that was really starting to look at high-rise from the perspective of the fire service in terms of their capability to reach these buildings from the outside with their aerial equipment. So we decided to look at on the other side of the Atlantic, and one that really appealed to us and ultimately appealed to Dublin City Council was Ottawa, or the Ottawa Fire Service's definition of tall and complex. And they said, again, in compliance with the British outlook, a structure that is beyond the reach of fire department aerial equipment because of height, setback, or location, structures that require unreasonable evacuation time, structures that pose a potential for significant stack effect, and I'm going to be talking about that later in more detail, and then structures which require high-rise tactics. So this could be buildings like hospitals, nursing homes, or buildings that have firefighting shafts with provisions for the fire service to use. So that really opened up everyone's view, and Dublin City Council were much happier then. Instead of calling it high-rise, they were much happier with calling them tall and complex, and so are we. So the key connection really between different sides of the Atlantic, from a firefighting perspective, the reach of available aerial equipment really presented as the principal metric for defining a tall and complex. So the next obvious question was, well, what can we reach? Well, the tallest ladder or aerial device available in Ireland right now is a 30-metre turntable ladder. And that's effective reach when you allow for where the driver has to position it and allowing for an angle that we can actually climb it is exactly 20 metres. So that really kind of contrasts greatly with Dublin City Council's understanding of what low rise is, up to 28. So given the broad variance in design and function of tall and complex buildings in Dublin, we needed to further refine our classification of these buildings from the point of view of emergency planning, working out how many people we needed to send to fires in these different types of buildings. So we broke them up into 3 categories, and we said a type 1 is 20 metres or less. And these buildings we can reach with our aerial appliances. And in the terms of their fire safety provisions, they will have protected stairwells, they'll have smoke management systems. They don't actually need to have rising mains. The type 2 we suggested is buildings over 20 metres, meaning we can't reach them, and they would be residential only. The fire safety provisions provided would be to a certain height dry risers, firefighting shafts, firefighting lifts, and if they're over 30 metres, they probably get a sprinkler system. And if they're over 60 metres, they would probably get a wet riser. And then type 3, we said is a combination of either all commercial or mixed development, and it would have very similar features to the type 2. The big difference from our point of view is the introduction of open plan office areas, which really changed the way we put out fires. So we'll talk about that later. So the next section I would really like to talk to you about is our problem with fires in tall buildings. And the first thing I'd like to place a little bit of emphasis on is fire behaviour in these buildings. So just to refer back to my background, I trained in Sweden in compartment fire behaviour, and I would have thought up to the point I got involved in this that I had a really good understanding of how fire actually behaves within buildings. But to give you some background knowledge, Dublin Fire Brigade had a really solid culture of educating firefighters in the very latest understandings of fire behaviour. But it's probably fair to say their education was focused on fire behaviour in single residential style compartments, because that's where we do most of our work. The fire development or the fire behaviour models that we used, and I believe you guys use as well, is based on the assumption of good mixing of fire gases and relatively uniform fire gas temperatures in the compartments post flashover. And fires in tall and complex buildings are now discussed in our world in a wider context of the building's actual construction features and the impact of a broader range of variables on fire behaviour. So the question then would be, well, what are these variables? And the first thing I'd like to talk to you about is internal fire and smoke spread in tall and complex structures. So the first thing I would say, and this would probably be very much bread and butter to you guys, is ineffective compartmentation, really brought about by vertical shafts, unprotected service openings, ductways, faulty fire doors, and so on. But I would just like to add this short film to kind of broaden our understanding. So this short film comes from Sweden, and it describes fire behaviour inside structures that would produce chimney and trench effects. So what they used to demonstrate this was basically two pieces of wood configured in a tubular fashion, one with a U shape and one kind of enclosed. And they started a fire at the bottom of these type of structures. And these would represent stairwells, ductways in tall and complex buildings. So the first thing that we noted when we looked at this, particularly in the one without the four sides in it, was the speed that the fire developed up this type of trench. Now, some of you might be familiar with this because this particular phenomenon was discovered in the King's Cross fire, where fires were developing up escalators at an incredible rate that hadn't really been characterized before. The fire on the right-hand side would be fires developing in shafts, ducts, in some cavities and so on. So the first thing that we noted was this was not behaving like our understood model of fire behavior, where you had initial fire growth phase, a flashover period, fully developed fire, and a decay phase. So moving on from that, the next thing that we started to discover was unusual smoke pattern or smoke movement in tall structures. And it's described very well as stack effect, on the left-hand side being the winter stack, which really conforms to our understanding of smoke rising. And what really struck us is when we looked at summer stack, where the smoke was inclined to go downwards. So from the point of view of identifying areas to evacuate in a building, depending on obviously the height of the building and the time of the year, and specifically the temperature differential from the inside of the building against what the ambient temperature was outside, we could expect smoke movement that was totally foreign to us. And when we were evacuating these structures, we realized we had to think about this quite differently. The next thing we wanted to talk about was lifts and lift shafts, and the understanding of smoke movement when we're using firefighting lifts. In essence, the piston effect of the movement of the lift will draw in smoke as the lift is going down, very similar to a syringe and a plunger within a syringe. And as the lift goes up, it was causing smoke to be pushed up into different parts of the building. Now, bearing in mind that the normal lifts will be out of function during a fire event, but we will be using the firefighting lifts an awful lot during our operation to move firefighters, equipment, and to move injured people down. So again, smoke coming out on floors that we weren't anticipating was something that we had to make people aware of. The next thing might come as a surprise to people in your profession was the impact, or if I was to put it more succinctly, the negative impact of smoke management systems and ventilation systems within tall and complex buildings. And I refer, of course, to smoke shafts and automatic opening vent systems. So the first thing that we really want to bring to the table here is the understanding of a concept called ventilation flow paths, and the preponderance of pressurized fire gases to seek areas of lower pressure to move to. And the areas that they want to move to most readily is the systems that are put in place to actually smoke propagation in the buildings that we're trying to protect. So I'm going to show you a ventilation flow path coming from the bottom of a stairwell to a ventilation opening at the top of a stairwell. So the first thing you will note is that the smoke is turning 180 degrees. and it's moving up the stairs, and very little smoke is actually moving out to the vent that's obvious on the right hand side, the door that's open. And the smoke is most likely to depressurize towards the tallest or the highest vent. Now, as the smoke layer heats up, it's going to ignite, because an awful lot of people don't realize that smoke actually burns. And you can see a very clear ventilation flow path forming of the fire gases moving towards areas of lower pressure. And what I would like you to picture in your minds is this event occurring where an apartment is left open and the smoke is actually, and the burning smoke is moving towards AOVs and smoke shafts. So this is a better indication of what I'm talking about. On the picture on the right, you can see an automatic opening vent, and the picture on the left showing a smoke shaft. This picture represents a fire we attended in the metro in Ballymun. And what I'd like to bring to your attention is the smoke management system malfunctioned. And if you look at the amount of vents that opened, and now picture in your mind how that is going to draw heat and smoke towards those vents and create a very difficult situation for firefighters. If a firefighter was to leave a firefighting shaft and a smoke shaft was functioning, or the door was open into the firefighting shaft and it was feeding the AOV, the flame and the burning smoke will be moving towards the firefighter. And we would suggest that the smoke shaft is in precisely the wrong position to support firefighting operations. They're placed near the building core, usually for financial reasons and ease of construction. And we would suggest that they should be actually placed at the furthest point away from the stairwell. The next thing I'd like to move on to is the exterior influences on fire and smoke spread, and specifically the effects of wind. I'm going to show you a film of a fire that we attended in Fenian Street. If you look carefully, the wind is very clearly moving from the right to the left, and there's firefighters inside that building now. You will listen now, and if you wouldn't mind listening to when the pump fails, and I'd like you to observe what happens to the fire. You can hear the pump change tone. I would like you to observe the changing colour of the fire gases, and I would like you to observe the angle that the flame is leaving that exhaust vent. It is not following a typical Coanda effect. The flame is moving out horizontally. What I need to tell you about that fire is that a policeman, a Garda, actually broke a window on the upwind side of that fire. And when the vent through window failure opened on the opposite side of the building, basically what you are seeing is this, the flame coming out horizontal. What I would like you to imagine is if the wind was blowing the opposite direction and the actual flame would actually come back at the firefighters, which I'm going to show you later. Wind-driven fires are not uncommon. And at the same fire I showed you earlier at the Metro Hotel, I would like to draw your attention to the flame leaving here and here. That is a wind-driven fire, and that's precisely because the automatic opening vents malfunctioned and they created the flow path that I described earlier. This is a sign of a wind-driven fire. If you look at the pulsing coming from the window, the wind is blowing into that room and the door of that apartment is closed. What you're seeing that looks like a belching effect is the wind pressurizing that room and the overpressure coming back against the wind. I would like you to imagine if a firefighter was coming from the other side and this happened. And you would end up with this here. This is a wind-driven fire, and as you guys would know, there wouldn't be a huge fire load in a corridor or a lobby for that matter. And what you were looking at was the burning fire gases in a blowtorch effect heading towards a smoke control mechanism. I would like to move on to exterior or external fire and smoke spread, and I would like maybe tell you something you probably already know. There's 6 types of external smoke spread, and the Coanda effect probably describes the phenomena very well. But I would like you to consider combustible window sets, external ACM or MCM wall cladding rain screens over combustible insulation. I would like you to consider external rendered wall systems or high pressure laminates over combustible insulation. I would like you to consider in commercial buildings glass curtain walls. I would like you to think about combustible balconies with high hazard storage. And I'd like you to look at these in a bit more detail. The picture on the right is a typical Coanda effect, where flame leaves a structure without the influence of wind and hugs the structure. And we like to show our children in the fire brigade a spoon and under a tap, and the way the spoon wants to be drawn into the flow of the tap water. And on the left is a pretty good graphic of a Coanda effect. The first, shall we say, structural component that we are now considering greatly is combustible window sets, including combustible transoms. You're looking at the Lacanal house fire in London in the picture, which was renovated 4 weeks before the fire, and the people who died stayed in place at the behest or instruction of the fire service. The next one is exterior fire spread, which is pretty much well discussed now. External ACM or MCM wall cladding, rain screen over insulation. This one is not as well noticed in the city as it should be, because it's rendered over insulation that's combustible, and it looks particularly, shall we say, standard finish to a lay person like myself. The curtain wall phenomenon is common in that if the curtain wall is installed and fire stopping is not installed here, instead of having this nice fire stopping function here, we get the fire moving from floor to floor up along where the curtain walls are actually attached to the building. A very common one now is people using their balconies for an exterior living space. This particular one is the fire that I attended personally, and the fire started here, where the owner of the apartment was having a barbecue, and he used some accelerant to get it going, and the fire actually caught onto the fascia soffit, and when it got into the attic void, there was no fire party walls, and we lost an entire block because the building wasn't finished properly. So if you take a look at this representation, what we're seeing here is internal fire spread through cavities and voids, through people not leaving or closing fire doors, and you're seeing some smoke moving up along the building, showing a typical Coanda effect. So if you were to consider all of the influences we've discussed on internal and external fire and smoke spread in tall and complex buildings, and add in poor construction and maintenance, the chimney and trench effects we discussed earlier, the unusual smoke movement, the unusual smoke patterns, the impact of smoke management systems, the failure of compartmentation, the effects of wind, and now add in combustible exterior cladding systems. Now, I should warn you in advance, I'm going to show you a video, and some of the language is a bit choice, but I think it's useful to understand when you combine all of those variables.
Fire Brigade? Yeah, hello, hi, in the fire, flat 16 Greenfield Tower. Sorry, a fire where? Flat 16 Greenfield Tower. The Fire Brigade are on their way. Are you outside? Yeah, I'm outside. Yeah, well, the fire engines are on their way. Just tell me how many floors you got there. It's the fourth floor. Right, okay. Quick. They're on their way already. Yes, I know it's burning, but they are on their way. You've only just called, as long as you're okay. Yeah? Okay.
Fire Brigade! Look, the house. Yikes. Going up 2 floors and coming out the 7th floor above the gym. It's going.
That's going, they need to get up there, that's not fair enough.
Oh, block 1. Look, at Grenfell Tower at like 1:30 in the morning. Fucking hell, fire, and that's getting bigger and bigger. People are gonna die, and I'm scared.
Man, you see that shit pull up? Wow. Go! Wow. It's gonna go right to the top of that building, isn't it? Oh my God. It's gone all the way.
And there's instant lights in there.
The thing is, this was the world changing for the fire service, in that the concept of defend in place or stay in situ was suddenly called into question. And when we looked at this more closely, it certainly wasn't a unique event. And when we looked at it even more closely, looking at 3 of these exterior combustible cladding fires, Grenfell was one of the slower developing fires, and the fastest one was in Dubai in 2015, where the fire was actually moving at 5 floors per minute. So what I would like to say to you is that we've very strong association with the British Fire Service, and we've very close contact with them. And to suggest that this is anything other than a game changer would be underestimating the impact that this has had on all of us, and I'm sure all of you. So before kind of showing you where we went with that thought process, I want to finish up fire behaviour in open plan enclosures. So the first thing I'd say is standard engineering temperature curves are developed using small scale tests. So this is pretty much a typical temperature curve, and if you look on the left hand side, we have to accept that size matters, and that the fire tests that we carry out, because of cost reasons, are usually carried out in 3 metre high square compartments, which the information then is extrapolated to bigger buildings in open plan. So for the most part, it's not true real fire tests. So the design of these buildings is based on a lot of engineering assumptions. What we'd like to add into your thought process is the complete revolution in materials that has occurred in the last 25 to 30 years. And if you were to look at that picture there and look at the amount of plastics and look at the amount of synthetic materials that we surround ourselves with now, and a huge amount of investigation has gone into how they behave by Underwriter Laboratories in the United States. Where we are now, and this is from academic research, is that we know that the modern furniture and contents of these buildings burns 5 times faster, and it gives off 10 times the amount of heat release that the original cotton and linen, horsehair and traditional materials gave off in the 60s and the 70s. So the actual fire behaviour in large enclosures doesn't actually mirror compartment fire behaviour. These fires actually burn simultaneously. They don't burn simultaneously across the entire floor plate or enclosure. They tend to burn over limited areas at a time. They tend to burn across floor plates towards openings and vertically between floors. And this type of fire behaviour has been labelled as travelling fire or progressive burning. This is something we did not teach firefighters up to about 6 months ago. Travelling fires, in the flame front spreads around the floor plate towards the openings we talked about already. As it travels, the burn consumes the flammable contents, but there's no cooling effect behind the flames. So smoke ahead of these flames preheats and post-heats the structure, causing it to lose strength. And this is a pretty typical example. The potential of travelling fires is to move at 22 square meters per second, and that's equivalent to a room every 30 seconds. So I'm going to show you an old test film that was done about the stardust. And at the time, the knowledge of fires was based on compartment fire behaviour. And this was actually sent around the world as a flashover. But what it actually was, when you look at it with a new set of eyes, is a travelling fire. So when I play it, I would like you to note the preheating of the fuels in front of the fire, and then the acceleration of the fire across the fuels that are in front of it. What you should always also note is that the fire starts to get quicker and quicker, and it moves like a tsunami wave. And this is actually a travelling fire. It's not a flashover as it was described in the era of the Stardust tragedy. And you can see that this fire ran out of control. So that is a really good indication of what will happen in an open plan design. So having put the fire behaviour concepts behind us, and really it helps us now inform what the operational challenges for the fire service in these buildings are. And first and foremost is the obvious, the height and complexity, in that access to floor levels may be beyond the reach of our aerial appliances. And if you look at the Grenfell tragedy down here on the right, you can see that's the highest the aerial appliances could actually reach in that fire. So what this actually means is that it limits the fire service operation to interior operations only. So in effect, the concept of us treating a fire as a defensive stay out operation has been eliminated. We have to commit firefighters, as London Fire Brigade found in the Grenfell disaster. So the next component from our point of view is firefighters are faced with considerable physical challenges to transport and deploy resources. In a normal fire, we can walk outside and the fire engine, which is a giant toolbox, is easily accessible. Our guys may have to climb 20 floors. Now, I'll give you an idea of what they're carrying. The personal protective equipment you're looking at there, the trousers, the boots, the upper part of the assembly and the helmet weighs about 12 kilos. The breathing apparatus weighs another 12 kilos. That brings you to 24, and the firefighters have to carry 20 kilos up with them. So that's 44 kilos, and say climb 15 to 20 floors before they start work. The next thing I'd like to talk about is a concept called reflex time. Bear in mind the standard time to flash over that's discussed is about 3 to 4 minutes. And bear in mind, in an open plan fire, and that fire can consume an area of a room every 30 seconds. From the time it takes us to arrive at the fire and go up these floors, it can take up to 20 minutes to get water on the fire for a well-trained crew. It can often take longer for us to travel from the ground up to the fire floor than it did for us to drive from the station to the building on fire. So firefighters then have to climb several floors or traverse long distances before they can even reach the fire floor. So what this actually means is fires have the potential to develop and spread to a much greater degree before effective intervention from ourselves. The next big challenge is communication and the extensive use of steel in modern buildings, and they act as a Faraday cage. So what that does is it prevents our radios working in these structures, because the Faraday cage effect stops radio signals going from one floor to the next. So communications to residents by operational crews is actually near impossible, because most of the buildings don't have a PA system as they do in the United States. So we can't give advice to the residents whether they should stay or whether they should go from the incident commander on scene. So we don't install PA systems. The next thing acts as a considerable issue for us is command and control. The size and complexity of these incidents require a huge amount of firefighters. Now, I'll give you some idea. An average house fire, you would have 12 firefighters at it. The Metro fire had 67 firefighters at it for 3 hours. And to try and organise command with difficult communication is extremely challenging for incident commanders. And our experience to date is that we do find difficulty in managing our resources, and we're having to change our practices to cope with that. What I would like to move on to now is the fire safety features provided by the building regulations, but from a firefighter's perspective. So the first thing is that firefighters depend on the functionality of fire safety features in these buildings far more than low-rise buildings, because if a firefighter gets into difficulty in a standard 2-story house, he can literally run down the stairs. We can't do that in these buildings. I'd like to point out where I've just drawn some circles there, and I'd like you to take note of where we position dry and wet rising mains. So if you're in this stairwell here and you want to start a firefighting operation into this corridor, we have to open a fire door to get to that fire, which allows smoke go into the stairwell. If you look at this picture on the left-hand side, if that is filled with smoke before we arrive because somebody left their door jammed open, we cannot use that riser because we have to put firefighters into a smoke-filled corridor before we connect up to a water supply, which is unsafe. So what we tend to do is plug into the floor below, which means we plug in here, we open that fire door, we head up the stairs, we open the next fire door upstairs, and then we go in and try and fight the fire. So you can see immediately we're compromising the means of escape that other residents might want to use to leave the building. And that's precisely what happened in Grenfell. Have a look at this video. This is in New York, and you can see when the firefighter forces the door, smoke fills the stairwell. Sorry, fills the corridor, which means the occupants on that floor cannot leave. Smoke management systems cannot deal with that quantity of smoke. They're designed to deal with a smoke production of the door closing behind the offending apartment. They're not designed to deal with actual quantities of smoke produced by real fires. The next thing I want to talk about is compartmentation. Our ability in the fire service to control this fire is heavily dependent on the standard of construction and the fire safety management of that building post-construction. This is a fire I referred to earlier. This is Lakanal House in London, and you can see that the fire started here, and you can see that the fire has spread up multiple floors, despite the fact that that building was renovated 4 weeks before that fire. The other aspect about compartmentation, and this is the Metro fire again, these are residential apartments, and the fire compartmentation fails, and this is by regulation, after 30 minutes between each apartment, which means that we're dealing with open plan fire behaviour, not compartment fire behaviour. And the likelihood of travelling fires is increased because the compartmentation isn't designed to last any longer on that. This is a 2-floor fire, and you can see there's no compartmentation on this floor because it's burned through. There's no compartmentation on this floor because it burned through, and the fire spread because of opening smoke management systems. The next thing I'd like to describe is the dry and wet rising main systems provided in different sets of legislation. The dry riser systems can be compliant with BS 5306 or BS 9990 typically. The minimum static pressure in these systems is that we can actually put into those pipes from air pumps is either 10 or 12 bar, depending on the standard that's used. Wet rising mains can follow similar standards, and they have pressure limiting devices on each outlet at 5 or 8 bar, depending on the standard. And these limit the amount of water that we can put on the fire, which I'm going to talk to about in detail in a moment. Interestingly, there's no requirement whatsoever to mark the dry rising or the wet rising main which standard has been applied. So when we arrive at that building, we don't know whether it's designed to BS 5306 or BS 9990. So we have to go with the lower pressure. This is a big problem in England. Fog nozzles will not function reliably in dry and wet rising main systems. Surprisingly, perhaps from an engineering perspective, fog nozzles are the standard type of nozzle used for firefighting in the modern era. All our firefighting techniques, which came from Sweden, are predicated on the use of fog nozzles, and we cannot use them using dry and wet rising mains. The next thing we have a problem with is the amount of dry and wet rising mains that have to be installed. The standard in the building regulations is 1 rising main for 900 square meters. The flow rate required to extinguish a fully involved 900 square floor plate is 5,400 litres per minute. So you can see there's a serious shortfall in the water supply that's actually regulated for. So the flow rate that we can actually get from dry rising or wet rising mains is 1,500 litres a minute maximum. So we're going to talk about now building a residential tall building, and the guidance documents commonly are typically in use as TGDB. It's superseded, as you guys know better than I know, by BS 9991 2011. In these documents, stay put is explicit. It's not a notional idea or an a la carte idea, it's actually explicit. And this design philosophy impacts on the number and width of stairwells required in these buildings. So the minimum width, as you guys know, is 1.1 meters. And if you look at the guidance documents that I've actually referenced there, stay put is actually not tacit, it's explicit throughout the document. So how does this engineering stay in situ strategy interact with the Irish fire alarm standards? Well, let's have a look at the British and the Irish. Well, in Ireland, the L3X or the LD1 standard looks for localised smoke detection in each apartment. That's not connected to the fire alarm system. So what that means is, if smoke develops in an apartment and the apartment fills with smoke, compromising those residents, it doesn't have to show up on the communal system in terms of the addressable panel, or it doesn't have to sound anywhere else in the building but the apartment. There's a heat detector, you guys know, in each apartment, which is set at 70 degrees centigrade. They don't always go off. On the UK system, they've localised smoke detection and alarms. They've no communal alarm system built into their apartments, and the communal alarm system is based in common areas only. So what does this mean? Well, okay, engineering stay put strategy is embedded in BS 9991. This standard facilitates narrow single staircases in tall and complex buildings because there's no need for everyone to evacuate. And then the Irish standard encourages a full simultaneous evacuation, which is a direct contradiction with the designs of the means of escape. So what does that mean? A real world example. This is an apartment block in South County Dublin. It's 16 stories. There's a single stairwell. There's 4 apartments per floor. There's a wet rising main. There's an L3X standard. There's a smoke shaft in the corridor, which we discussed earlier as problematic. And the controls for the smoke shaft are in the corridor. The AOV is a supply air system in the stairwell, and it's a 2-story below surface underground car park. Here's this building. This is a building designed to a standard that supports stay put. This is a building that has an alarm system that encourages full evacuation. Looking at the width of that single staircase, can anybody listening to me make an argument that people could leave that apartment block while we're going up? Or equally, do you honestly think that we could mount a firefighting operation with a staircase that looks like that? So the escape routes that we're most likely to encounter are going to be heavily congested with evacuating occupants during our operation. This could compromise both the evacuation and the firefighting operation. So to be honest with you, if I was being diplomatic, I would suggest that this is suboptimal. After the Grenfell inquiry, a very eminent fire engineer from Ireland called Barbara Lane gave evidence, and her evidence contained this statement: there is no building regulation requirement to provide active or passive fire protection measures which would allow an alternative to a stay put strategy. I think that's an extremely telling comment, and I think it's something we should all reflect on with regard to Irish standards. So where are we now? Well, okay, we have, as an American politician said, we have known knowns and known unknowns. So in terms of an anticipated notional 100 life of a building, the influence of fire safety management is by far the biggest influence. So if you look at this tiny little slice, that's the construction. And the rest of the building life is down to how the building is maintained and managed. So the first question we have to ask, how well do our buildings comply with the regulations and the design intent? How good is the fire safety management post-construction? So it's clear we don't actually know. So in terms of a summary of the operational challenges, we have a big issue with stay in situ, and it's an engineering strategy. It's not a fire strategy. We have a big problem with the smoke control systems design. We have a serious, shall we say, reservation about dry and wet riser design. And then we have misgivings about our understandings of how well the buildings are being managed post-construction, and foundationally, how well they're built in the first place. So you can see our dilemma. So you might ask a question, what did we do about this? Well, the first thing we did is we took a really hard look at ourselves, and that's not as easy as you think. To look inwardly and critically is never easy. And we decided we needed to have a benchmark of where we needed to be. So we spoke to our international colleagues, and interestingly, we didn't speak to London Fire Brigade. And it'll become clear in a few minutes why. We carried out an academic literature review of international best practices, and we identified realistic high-rise emergency planning scenarios. We then undertook over 2.5 years, over 20 full-scale exercises, and anybody that would let us into their buildings. And we performed a gap analysis of where we like to be and where we were. And just to give you an idea what we've done, this is quite unique internationally, is that we've actually got some emergency planning scenarios that we need to train to achieve a successful outcome against. So from an engineer's point of view, the assumption is that everything is going to work, even though I do accept there's a layered approach to fire safety strategies, but there's an acceptance that everything's going to be maintained and people are going to behave in a civic spirited way. But from a fire service point of view, you might suggest that we're slightly paranoid, and we expect people to behave like Homer Simpson, to do silly things and to do things against what they're expected to do. So the first scenario that we are training to now is the stairwell and attack corridor are smoke-free when we arrive, and there's no impact of wind. The second scenario is the smoke-free stairwell is going to be there, but the corridor or lobby is going to be contaminated with smoke because somebody left their front door open or wedged it open, or perhaps it burned through. The third scenario is smoke ingress to both the stairwell and the attack corridor. This would be in a building that has poor fire safety management and we've door wedges all over the place. Scenario 4 is a wind-driven fire. Scenario 5 is a commercial open plan fire. Scenario 6 is building failure. Now, this is really at the leading edge of emergency service thinking internationally, in that we're now teaching our fire commanders to look for indications of when a building's facilities, structures are actually failing, and our strategy should go from a firefighting operation to a full emergency evacuation. And I'm sure that resonates with anybody who studied the Grenfell tragedy. The 7th scenario is underground car park fires, with particular emphasis on electric vehicles. We could actually do a conversation about them on their own tonight, but suffice to say, extremely problematic. So what did we do then? Well, we really got involved in the development of key principles for tall building operations. And this was driven by a wave of operational intelligence that we really need to get to know the buildings that are out there really, really well. The concept of rapid intervention, as quick as anyone in the world at getting water on these fires. The concept of simultaneous fire attack and phased evacuation at every instant. I would hope you would look at the last one there and consider stay in situ engineering strategies, because I'm going to talk about the last part of that in more detail. So we noticed some development opportunities in our own skill base, and that's the code for things that we were really crap at. And the first thing was to make sure we adopted evidence-based firefighting tactics. We needed to improve the way we gathered and disseminated operational intelligence about the buildings. We needed to minimize the reflex time to get water on the fire. We had to enrich our knowledge of how these buildings are being built nowadays. And then we had to develop skills in deploying hose in very, very confined areas. And I showed you a video of how small those areas are in firefighting shafts. We also had to get good at working firefighting lifts. They seem like a brilliant idea, and they are, but they have a huge amount of danger associated with their use, and we had to get good at managing those hazards. And then we had to adapt our firefighting and rescue techniques to suit a new built environment. And we had to improve our staff understanding of tall and complex building fire behaviour. We also had to develop tall and complex EMS operations. So just to give you a simple configuration in your minds of that, if an ambulance pulls up at a tall building on fire, Can the ambulance crew go into the building to help somebody? No, they can't, because they don't have breathing apparatus or firefighting gear. So we had to develop contingencies that we as Dublin Fire Brigade would act as the pre-hospital care within burning buildings, which again is quite unique internationally. So how do we enhance our effectiveness? Well, we started using evidence-based strategies for command and control. And the key element of this was prescriptive tasking of arriving resources. And what that meant was, when I normally would go to a fire and take command of, say, a 4-pump fire, I can be quite flexible how I use those resources. The sophistication of firefighting operations in the taller buildings require predetermined, sophisticated tasking for our assets as they arrive sequentially. In other words, a pre-plan what the first arriving appliance, the second arriving appliance, and so on need to do. We also had to establish localized command hubs, and we had to pre or front load this concept, in that we front loaded command hubs in the lobby, the bridgehead, a planning and logistics officer. And you might say, where does that come from? Well, to give you an idea, if we had 25 or 30 firefighters up there with their SCBA sets on, they've 40 minutes of air. So we've 40 minutes of firefighting. So we had to have a system for resupply of air cylinders from the get-go, which we don't have to do at ground floor-based fires. The next thing we had to do was improve our command and control. And if you have a look here, and I know it looks like a spider's web, that is a typical command and control layout at a tall and complex incident. And you can see straight away there's a lot of people, there is sophisticated radio nets, and it's altogether a different concept. We had to learn how to deploy our vehicles differently. Because there's so many fire engines needed for these incidents, we had to start parking the resources a block away, and rather than clutter up the fireground and limit ambulances coming in and out of the area. So we had to learn how to deploy differently. We had to develop fast, frugal heuristics. In other words, flow charts or decision support tools for the incident commander. The tactical complexity of dealing with these fires, I haven't got time to explain here. So we had to actually equip our incident commanders with very simple checklists so they could figure out the best way to deal with the event tactically. Moving on from this application of evidence-based firefighting, we were using research in basically Underwriter Laboratories in the United States who have produced a suite of research documents into firefighting tactics. And we found them extremely useful when we had to convince ourselves that change was necessary, because the material is peer-reviewed academia, and it makes convincing a non-believer much easier when you have academic material to support change. The key strategy for Dublin Fire Brigade at these buildings will be the concept of a simultaneous rapid fire attack and a phased evacuation strategy. And we found that this would offer the greatest utility. And we will not be going with stay in place. Now, that's a very key policy decision by Dublin Fire Brigade. We don't have confidence in the buildings. We don't have confidence in the compartmentation. We don't have confidence in the maintenance of the buildings post-construction. So how are we going to achieve this fast intervention? Well, we change the way we deploy hose. If you look in the bottom right, you will see a smooth bore nozzle. We gave up on using this in the 1970s, using modern techniques, but because of the rising main systems, we had to go backwards to achieve an adequate flow rate. We had to standardize the equipment brought up, and you're looking at the standardized high-rise pack that every crew going into the building carries. It necessitates the movement of a large amount of equipment, but it means we don't have to send people back down looking for equipment at 20 floors up. I'm going to show you an evidence-based tactic please take note of the angle that the water is being applied. It's particularly fast, and it's a technique developed by Underwriter Laboratories, and it's a technique we've adopted. It's called transitional attack. Again, we had to go backwards with the smooth bore nozzle to achieve an adequate flow. The next thing we've actually incorporated, and we had this in place before Grenfell. The single biggest criticism that was placed on London Fire Brigade was that their movement of firefighting shafts necessitated the opening of fire doors, which meant that the firefighting shaft became filled with smoke and people couldn't use the escape. So we quickly realised we had to come up with a solution for this, and we purchased this equipment here. So if you look at the top picture, it's called a smoke curtain. So this is a portable device on a frame, excuse me, that we can mount on doors as we go on to corridors, which stops smoke going onto the stairwell. And if you look at the bottom of the picture, you will see an electric positive pressure ventilation fan, which allows us to combine the two concepts and pressurize the actual stairwells. This is the smoke curtain. It is literally a revolutionary concept which was designed by Professor Michael Reich in Germany, and it allows us overcome the problems presented to us by the design of firefighting shafts. This is a smoke curtain that we actually used at an incident. It was a hospice, and this is the escape route in the bottom picture. This in the top is the actual fire compartment, and this picture shows you how effective the use of the smoke curtain is in preventing means of egress being contaminated with smoke. Positive pressure ventilation fans will allow us create a positive pressure in the firefighting shaft, which will also assist in maintaining means of escape. We realised that if we bought the biggest aerial device in the world, the floors available in modern construction in Dublin will always be taller than the capabilities of that ladder. So we bought another piece of equipment. This is a floor below nozzle, which we can effectively put water on the fire at any height, because the curvature in this nozzle allows us simply use it from, as the name suggests, the floor below the fire, even if it's higher than the turntable ladder's capability. The next innovation for skill development, if you look at the bottom of the picture, is the use of XVR. It's a virtual reality training software for teaching our incident commanders, and that's one of the simulations that you're looking at the bottom. And the next part of our skill development will be the design and construction of a high-rise structure, which will be built probably after I retire, but it's due to be built in 5 years' time in the training centre, along with the structure for the metro system tunnels that we're going to be dealing with tram fires underground. So in summary, and I know I've been controversial and at some stage maybe even adversarial, I'm just going to give you the main ideas here. The current city planning documents confirmed the intent to consolidate and expand the city through tall and complex development, effectively high density development. Dublin Fire Brigade have a clear understanding of the challenges that present for firefighting in these type of buildings. And we've developed honest development opportunities for improving our operations in these structures. And we're currently rolling out that skill and that knowledge that we need to serve the people in Dublin. So I'd like to thank you for your patience and probably your good wit when we discuss this later. So thank you so much.
Thank you, John, for a very insightful and indeed sobering presentation. There's a fair tour de force of I guess the state of the art, and certainly an eye opener for me in many respects. I'm going to open up to the floor for questions, and Victoria, I don't know if there's any questions in the chat, but I think if you can raise your hand if you have a question, we can switch on your mic and you can ask it directly.
I don't know if you saw that there, Paul. It's a bit of feedback in terms of hand raising. Yeah, I think if you hit mute, hopefully that'll work. John, you might hit mute as well, just for a second.
Sure thing.
I think we might be turning it on and off. Yeah, that's better now, whatever that feedback was. I was just going to ask, in terms of the maintenance of buildings was something you said obviously has a big impact on what the risk, the fire risk, and your firefighting capabilities. Is there anything? Are there any particular examples in terms of poor maintenance that stands out to you? And do you think there's anything that as engineers can be done to build into the design to try and mitigate those risks?
Okay, section 18 and 19 of the Fire Services Act talk about the concept of the person having control of a building. Section 19 actually describes what is a potentially dangerous building because of certain defects. If you were to take residential buildings only and multiple occupants each paying a management fee, immediately you're into a grey area of who actually is the person having control and who's responsible for fire safety. And what happens is they generally ask a management company to take over that. But there's enough wriggle room that if a prosecution is being made, the fire service has no option but to prosecute the residents, even though they had no hand or act in the management of that building. So what actually happens? Well, what actually happens is, first and foremost, people struggle with the management fees, and then the management company haven't enough money to maintain the structures such as automatic opening vents, fire alarm systems, fire doors, and maintaining the required widths of corridors and so on. And typically what happens is, apart from the real high-end dwellings in Ireland, the buildings start to fall into disrepair, and they start to fall into the category of what would be legally described as potentially dangerous buildings. Now, it's our experience that this is not uncommon, and the concept of then what an engineer can do to stop that happening, it's actually very difficult for the people who design and construct them because they're long gone. So the only thing I can think of from a fire officer's point of view is if they change the law and they give clear lines of responsibility, who those persons having control actually are, and to set up an inspection regime from the local authority or even the fire service to make sure that this is happening. Right now, residential multi-occupancies are not being inspected by the local authority fire services. So there's no way of ensuring right now that these buildings are actually safe. So our experience then is that when we go to fires in not only the residential, but the commercial, the hotel, the office blocks and all the rest, the standard of construction, and I'm not saying the standard of design, is generally poor, so that we find smoke egress into areas of the structures that is very, very hard to predict. So to encompass your question into a reasonable answer, number one, I don't think the legislation is enforcing the person having control as well as it could. And secondly, the concept of people paying management fees throughout their life of their mortgage and beyond isn't really resonating with people very well, resulting in not enough money being available to maintain buildings. So we really have a big dilemma. And what tends to happen in this country and other countries, it takes a tragedy for legal change or for the way we go about our business. And unfortunately, I think that's quite possible. Does that answer your question?
Yeah, I think there's definitely food for thought there. Thanks, John. Paul, I see we have a few questions in the chat, maybe.
Yeah, I have a question from Lisa Eden. John, thank you, John. It was very sobering and an eye-opener. I think it will be for all structural engineers. Actually, I just add a comment to that. I think the video that you show is actually wonderful to see. And I think when people see the practical realities of stuff that goes wrong, we see it in our own, particularly more experienced designers because they spend a lot of time on lots of different sites. They get to see, I guess, the good, the bad, and the ugly. So you have a hierarchy of where maybe some of the limits are. So I just Lisa's question is, in designing all stairs for so stairs need to be designed for two-way flow in an emergency. Pretty much full stop. They do need to be designed.
Oh, that's a statement. I thought it was a question.
Statement.
Yeah.
Yeah. That's a given. You would absolutely.
Well, either that or have a second stairwell. Yeah. And obviously that's going to impact on lettable space and sellable space, which now you're getting into the economics of building a building, and I completely understand that. But the current stairwell configuration is actually designed around stay in place. And the alarm system, as I said earlier, is designed around full evacuation, which is not a great setup. Let's be honest about it.
Okay. Thank you. There's a question from Barry McGann. Which code of practice do you want the dry risers to be designed to?
Okay, I'll tell you what we want, and I don't really mind what legislation they call it. We want 150mm dry risers. We want dry risers that are capable of supplying enough flow and enough pressure to support modern firefighting tactics. So at the moment, one of the criticisms I've made is none of the legislation in this part of the world achieves the objectives of the fire service. And if you're not supplying enough water, you're going to lose more property. And if you're not supplying enough pressure, you're not going to be allowed to use modern firefighting equipment. So the corollary of that is, if we're using old-fashioned nozzles to put water on the fire, there's actually going to be more water damage at the smaller fires.
Okay. He has an additional question to that, and how big a stamp or label on each floor would be useful?
How big a stamp
or label? Is there? I think there's a stamp or label on the risers,
well,
so you can identify them easier.
All right. At the moment, there's no requirement to mark them at all. But like, I mean, we can get into the semantics of how big that marking used to be. But I believe that something that's highly visible and a very strong, shall we say, colour that will show up at night time, that the actual size, right, you can get into the people who are experts in that. But what I would ask for is a highly visible indication of what standard the riser is built to, or if it's a dry or wet riser, and what are the maximum static pressures that we can actually put into that pipe work. So that's really my response to that, to be honest.
Is there any more questions? If not, I'm going to ask one, John, and maybe a little bit controversially. When you think about development, there's always are designed to minimum standards, but to design to, like, if the finances and budgets for projects were unlimited, we could all do design, but there's a limit to what we can design, and with codes of practice in many respects, like not just across structures, across it, a lot of the design is done to perhaps to minimum, because that's the most economic cost, and because that's what people see. For me, this is one of the important reasons for lectures like this, is that it I suppose open minds to say the downsides that might have further down the line. But there's, I guess my question is, there economic pressure, perhaps from developers, or particularly with speculative development, where there's not necessarily a long-term view on that, on the building project. I'd like you to comment on that.
Well, I agree with everything you're saying. Maybe this should be driven by the insurance industry, because ultimately they're the people taking the actuarial risk on the end product. Shall we say, failure to enforce the maintenance of buildings. I wonder how the insurance companies would feel about that when they're carrying the risk. I wonder how insurance companies would feel if they found that the water supply can't actually meet the requirements for the actual fire development rather than a notional fire development. I would suggest that the B-car system is certainly going to help us some of the way with that. But on balance, if we continue with a concept that we just have to creep over the minimum standard to achieve compliance, we're always going to just employ contractors and maybe engineers that can offer these services to achieve that, and not levels of finish and levels of compartmentation that are actually required in the real world. So I agree with everything you're saying, Paul, but I think it's going to have to be really driven by legislation rather than commerce and self-regulation.
Okay, thank you. If there's no more questions, I'm going to ask Peter Finnegan to...
Paul, I think we've one more just in the chat there.
Okay, yeah, from Paul Tyson. Kent FRS in the UK have a number of 150mm rising fire mains in tall buildings with twin outlets on each landing. Had to be specially designed to old 1970s codes. Is this something that you see Dublin Fire Brigade looking for in high-rise and tall buildings?
Yeah, absolutely. The person behind that innovation, or retro innovation if you want, was Paul Grimwood. He's the principal engineer for Kent Fire and Rescue. When you go from 100 to 150 mil, there's a significant increase in flow rate. We can use more hoses more quickly, and we can stop, for example, an open plant fire moving across a floor in a travelling fire configuration with an adequate flow rate. I would wholeheartedly support the innovation by Paul Grimwood and Kent Fire and Rescue, and the actual expenditure would be minimal, because you're talking about a galvanized steel pipe and a couple of extra 65mm instantaneous coatings on each floor. So I would completely agree with that. And I'd go a little bit further, because I know Kent also have pushed this idea. They want the smoke shafts on the opposite end of the corridor, away from the stairwell, so that if a fire breaks out of an apartment or someone leaves the fire door open, that the smoke layer, the heated or maybe burning smoke layer, is actually being pulled away from the firefighters rather than towards them. So again, Kent leading the way, and I would have really good relationships with Paul Grimwood. He's one of the leading engineers in the UK.
That's great. Actually, there's hope in that quite maybe subtle changes or innovations might have a huge difference on actually performance. So yeah, there's some hope that we're not going to blow budgets or limit heights for future designs. If there's no more questions, I'm going to move on, conscious of the time, that we'll ask Peter Finnegan if he could offer a vote of thanks.
Hi, John. John, can you hear me?
Hello, Peter. How are you?
Hi, John. How are things? I think I possibly got you into this mess, John, but thanks very much for doing it again. At the weekend, we were looking through Netflix to look at horror films, and I say that the two films that still give me a chill, no matter how many times I see them, are the Grenfell film, and the other one, which is, you'll know yourself well, is the Bradford fire.
Yeah.
Because they're both fires that I think, as you're sitting there, you just know there's going to be severe consequences. And I think with the Grenfell, just as a building designer, I also got a chill, and I, I've read quite a bit about it since. I also, Paul rang me earlier on, and I said to him that I'd seen your talk already, but I haven't really. You've changed it a lot. You've updated with the Metro Hotel. You've the words that are just popping out as I'm making notes here is that you're constantly observing, you're questioning, you're skeptical, you're prepared to. You use the term performance gap knowledge, self-examination. You're questioning the conventional wisdom. And above all, you seem to be innovative, and these are all qualities that are exceptional and certainly greatly, we admire them in engineers, and certainly in your profession, John, they're to be greatly admired. There's a few things that worry me. yeah, another fire that you could have mentioned was probably the two multi-story car park fires, where the conventional thinking on fire spread was completely overturned due to the amount of plastics in cars nowadays. And then you showed the photograph of the houses and the amount of plastics we have. So that's a concern. You mentioned there at the end about insurance companies. I think possibly that would have to start with a questioning of what their objectives are. I think the objectives of Dublin Fire Brigade is life. I think depending on the nature of the building, the objectives might more be the saving property, and you could get a conflict in locating AOVs at all. And that's arisen from a discussion I had at an early stage of design over a building quite a long time ago. It bothers me as well that we're essentially designing to a code of practice with a stay put philosophy, and that allows us to put in single stairwells when in actual fact we want to be evacuating buildings totally. I'm interested in the comments about the steel frame, and I might talk to you again about that in another venue. I'm also, just a comment for yourself as well, John. Like, I'm involved generally in an early stage in building design, feasibilities, that sort of thing. And I would say at the moment, it's overwhelmingly dominated by energy considerations, zero energy. And I can't think of a single conversation I've had that I can remember recently where fire was a significant part. It's seen as something you got to comply with.
Yeah.
And you made a comment towards the end, as long as we take a minimum approach, we're going to have problems. So that's of great concern to me. And I think maybe our professions, like of structural engineering and also in particular architecture, I think need to do some self-examination and gap analysis. So with all those worrying thoughts, I do want to thank you for an excellent talk once again. You don't seem to lose any energy in giving the talk again, and I certainly didn't tire of listening to it. So on behalf of the IStructD and our members and all our guests, I'd like to sincerely thank you for a wonderful lecture, John. And I hope your words are lost on the audience. Okay.
Thank you very much.
Can we have a cyber round of applause? I'm not sure how that works.
I think one of the best ways to do it, if everyone could just raise their hand and we can do it that way. It's a shame not to be doing it in person. Look at it, all those hands going up. And I think, John, just to finish as well, I'd like to offer my thanks and say that we share some of your structural engineers, and I think inherently share your paranoia about what you can expect, because we've I guess seen again the good, the bad and the ugly. So sometimes and because it's about life safety, we have to be always a little bit pessimistic in our view. So with that, I'd like to thank you again and close the meeting by just reminding members that our next we have 2 more presentations set for the next year. John, you actually might be interested in attending these. On the 10th of November, we have Seamus Doyle of O'Connor Sutton Cronin presenting on the EXO building, which anyone who's been in Dublin any time in the last year, certainly any structural engineer would have their eye drawn to that building. And then on the 8th of December, we have the DAA control tower, which again, another prominent, I think the tallest inhabited structure, occupied structure, I think, in Dublin, is it? Perhaps in Ireland. So that's our next 2 lectures for next year. With that, I'd like to thank you all for your attendance. John, in particular, for a tremendous lecture. We do have it, I believe, recorded, and I think that recording will certainly be watched again and again, certainly from my point of view. So with that, I'd like to ask you to thanks again for attending, and stay safe and best of luck.
Thanks for the opportunity. Thank you. Bye now.